So we learned that in previous classes that if you have an outlier in predictor means x1 x2.xp. That means if you have outlier in x, for example, this red point is an outlier. The x-axis is x1, the y is like x2, and the red point is an outlier in x1, x2. So if that happens, then something called the leverage is high. How do you define the leverage? Leverage is the diagonal elements of the P matrix, P11, P22 to Pnn. The diagonal elements of the leverage. So the PII should be high if it's an outlier. Actually, we can see this if we open lecture 16 example 3.csv and form the proper X matrix, calculate the P matrix, look at its diagonal, then we see that the P31, 31 is much bigger than the rest. And we looked at another example where we see the similar thing. Our next topic of interest was outlier in response. And we know that outlier in response does not mean that yi is an outlier or yi hat is an outlier. It kind of means yi is not what it should be. So yi should be something like yi hat. If yi is not what it should be, that means yi minus yi hat is big. And by big I mean big, small, or yi minus yi hat, that's ei. Ei is big. I mean big positive or big negative. And we know that ei can be standardized as ri because EIs have different variances. So what's big for E2 may not be big for E5. That's why we have learned about RIs. So RI is called standardized residual for ith observation. And if now we kind of have the final answer. If Ri is an outlier, if Ri is big, like big positive or big negative, then that's what we're looking for, outlier in response. But later we shall see there is also trouble with that. So we look at lecture 16 example 2.csv, just one x and one y. Like here p equals 1, there's only one x variable. We are taking this because that's easy to show in the graph. So for this data points, we add one more data point, the red one. And the red one is at x equals 50. X equals 50 means it's an outlier in x. And y is 259.0539. So this y is like 20 distance away from the black line. So that's not too much distance. Also, the red point doesn't change the model too much. So the old model is given by the black regression line. The new model is being given by the red regression line. And we see that doesn't change much. Hence, this red point should not be an outlier in response. And it is not. Next, we add the green point. For the green point, x is the same, 50. So x is still an outlier. But now y is too much away from the black line. Y is 389.0539. So even if you see, just look at it visually, you will see that the green point is too much away. So this is what like this green point should be an outlier. And if we check the RIs, the command in R is R standard. We actually see that's happening. 3.77969. That's like a large value. Usually, if Ri is outside of the range minus 3,3, that is large by itself. Like that's considered large. So this green point shifts the model too much. That means the green line is too much not like the black line. It has shifted too much, and hence it's an outlier in response. We can actually also plot the RIs over here, and we see that for 31th point, the RI is truly large. Okay, so the RI for the rest of the points are over here. The RI for the last point, the 31st, is truly large over here. Finally, we just add one more point. That's the blue point. Now for the blue point, x is 15. That means x takes a value which is not an outlier. It's an usual value. Like it very much belongs to this range. So x is an usual value, x equals 15. But y, this blue point, is as much away from the black line as is the green point. So the blue and the green are kind of equally bad. They are both equally away from the black line. So the blue and the green should both be an outlier. And once again, we can check the standard residuals. We shall see that, by the way, this third column, column 3, is for the green, and we already know it was 3.7797, which was big, and hence we know like that's an outlier in response. For the blue, it's 4.0360, which also is big, and we also know that the blue is an outlier in response. But blue and green are kind of equally bad in some sense. They are equally away from the black line. So why is the RI more bad for the blue? That's one point. The standard residual is worse for the blue than the green. That's point number one. And if you go back to the plot, you see that the blue line hasn't changed much. The green line has changed quite a bit. So that can be easily explained. The green point has high leverage. That means it can change things much. Like a point with high leverage can change things much. Why does the green point have high leverage? Because x equal to 50 is an outlier, and for an outlier, PII is high. If PII is high, that means it's the leverage is high. So for high leverage, it has the ability to change the line too much. But the blue doesn't have high leverage, so it's not changing the line by too much. So what we just now saw, that sometimes a high leverage value can have a low, the third column, it has high leverage. So the RI here is big, but not as big as the blue one. So that's what I say. Sometimes a high leverage point gives a low or at least not so high RI. So the RI value for a high leverage point sometimes may not be as much high as we expect it to be. Like it may not show that it is bad. Here comes an example. So we have x1, x2, x3, three variables like p equal to 3, and we have an usual regression line. Y equals some linear function plus some normal error and then we fit the regression in R as fit4 underscore original equals lm y follows x1 plus x2 plus x3. Usual business. So there is nothing wrong with fit4 underscore original. Now we add an outlier to this data. It's an outlier in x. So at the end of x1 I add 15, at the end of x2 I add 50, at the end of x3 I add 100. So if you look at uniform 5, 8, 15 shall be an outlier. If you look at 15, 30, if all observations are between 15 and 30, then the value 50 shall be an outlier. Similarly, the value 100 is also an outlier. So first of all, the last point is an outlier in x. What is the y for that? Let me calculate what's the y hat. So yi original hat is the y hat according to the like it's y hat for the new point according to fit4 underscore original. Like fit4 underscore original has some fitted line. Yi original hat is according to that line, the y hat. Now what I shall do is I will make the new yi, like in this 2 lines of our code. What I did was this was the y hat, I added 100 to it, and I call that my new yi. So the yi for the new point, I use the word new yi, that's not like very nice. But what I mean to say is yi for the new point is what y hat should be plus 100. And this value 100 is big. That means it's kind of farther, like very much away from the black line. Like if you think the black line is the original, then yi for the new point should be an outlier according to that. And actually if we check the R standard, that means the RIs, we see that's not happening. The RI is 1.84. It has not even crossed 2, let alone like it's not even outside minus 2,2, let alone being outside minus 3,3. That's a problem. Okay. So what's the remedy? The remedy is something called the Cook's distance. So the formula for Cook's distance, I've written it down, but it's not needed for now. I only need to use it right now. And if I do use it, I will use it like Cook's.distance fit4. Like it's very simple. And that will give me the CI, like C1, C2, C3, C4, C5, all these. And finally C41. Now if you just look at the numbers, it may take a while, but you'll realize that C41 is truly big compared to the others. Compared, like 4.81 may not seem like that big, but if you look at the other values, they are like too small. So that means C41 is too big. If you actually look at the plot, that's obvious. So these are the CIs for the rest of the points. For C41, it's like this big. And that's like good. That means we have found a weapon, or we have found a formula, a measure, which will tell us if something is an outlier in response. So what we have learned so far is number one, if xi1 xi2.xip is an outlier, that means it's an outlier in x, then PII is large, and we say that ith observation has a large leverage, like it's a high leverage. If ith observation has high leverage, then two things can happen. So it's either influential or it's not. So that means we want to know whether ith observation is influential. What does the word influential mean? So an observation is influential if by its presence it changes the model too much. That means if you keep the ith observation, so that's one model by with keeping the ith observation, you don't delete that, versus you again fit the same model, but now you delete the ith observation. These two models are too much different. That means by its presence, it's changing the model too much. Okay. When that happens, that means the point is influential. I mean, the English is actually very accurate here. Influential, we know what it means. So how to detect if something like that's happening? First of all, we are looking at high leverage points, and how to know if that's like a influential point. A point with high leverage may not be influential, but how do you know if it's like influential or not? So first of all, you check the RIs, and next you check the CI. CI is the Cook's distance. That's it. So these two will kind of tell you what you're looking for. Our next topic is QQ plot. QQ plot is like it can be used in many situations, but we'll use in only one particular situation. It's like this. So if y1, y2 dot yn, these y's have nothing to do with the previous y's. Okay, these are just some y's. So if y1 through yn, we want to test whether they are from IID from normal 0, 1 or not. We know about normal 0, 1, standard normal. We want to know whether y1 through yn, they follow standard normal or not. There are many tools for that, but one popular method, a popular graphical method, is the QQ plot. And it goes like this. So I've written that code down, but it's like this. So it will be a plot over like this, and there will be a line in between. If the points fall along the line, then it's like good. It's from normal 0, 1. If the points are away from the line, it's not. For example, this is 200 samples from normal 0, 1, and the points are kind of close. These are 200 samples from T with degrees of freedom 5. The points are a little bit off. Okay, I mean, at the very end, it's like quite a bit off. If you see, like, although they both plots are of same size, but this kind of ends at 3 versus 3, and although this is like 3, this is like 4. It goes even above 4. So actually, it's like quite big. Both plots, because I've scaled it down, they look the same size. So as if it looks like equally bad, but they're not. They're not equally bad. So the right hand one is like worse, as it should be, because it's not from normal. It's from T with degrees of freedom 5. Now, here there are 200 samples, but if we decrease the sample size, so from 200 samples, if we make 40 samples, like in the next page, so once again the left one is from normal 0, 1, the right hand one is from T. We see that, like, except this point shows that it's bad, but the rest of them are like, yeah, quite good. So that's the problem. For small sample size, the QQ plot can't make out the bad guys. Okay. Now, how does it help us? So we know that our model is something like this: yi, the ith observation, yi equals beta naught plus beta 1 xi1 plus beta 2 xi2 plus dot 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 beta p xip. That's the linear part, plus epsilon I. That's the error for the ith observation, epsilon I. And epsilon 1, epsilon 2, dot epsilon n, they are all from normal 0 sigma square for some sigma, and they're IID. That means they are identically and independently distributed. So the assumption is that they are normal. If we want to check whether they are from normal, then first we find, okay, it's the same old friend, Ri's once again. R1, R2, Rn. We calculate them. And if things are good, then these guys should be something like, they should be from normal 0, 1. They are not exactly from normal 0, 1, but kind of they are. Like, they should behave as if they are from normal 0, 1. And if somebody is supposed to behave like normal 0, 1, of course, if I do their QQ plot, that means it should be a good QQ plot. All the points should be around the line. And in this example, it's a good situation. x1, x2, x3 as before. Y is a linear function of x plus a normal error. So I'm making sure it's a good situation. And I'm doing this plot. Okay. And we see it's like, okay, not bad. But then there's model number 2 and model number 3. In model number 2 and model number 3, everything is same. I do the x1 same way, x2 same way, x3 same way. Y equals, it's the same formula, but only thing that's changing is in model number 2, the error becomes RT n comma degree of freedom equals 5, and in model number 3, it's R Cauchy n comma 0 comma 1. So the errors from one are from T distribution and the other is from Cauchy distribution. And we see that produces bad effects. So the QQ plot is helpful for detecting normality.